Welcome to today's MeKo MedTech Materials webinar about NiTi. My name is Laura Denzer. I'm one of the project managers here at MeKo, and me and my colleague Kai Leimann are going to present MeKo in general, and in specific the different manufacturing possibilities we offer to our customers related to the material NiTi. Let's have a look at our plan for the next 30 to 45 minutes. First, I will start with a short company presentation and show you our processing capabilities regarding the contract manufacturing of medical devices. And after that, Kai will continue with the big part related to our capabilities to produce components made out of Nitinol. All right, so for the next 8 to 10 minutes, I will give you a general overview of our company. MeKo Manufacturing is a contract manufacturer. Specifically for laser material processing and also the related post-processes, as some of you might already know. It was founded in 1991 as a one-man job shop by Clemens Meyer-Kobbe, whom you can see on the right of the picture. Today, his son-in-law, Jakob Dose, on the left of the picture, is the operational CEO of the still family-run company. Our focus is on high precision and challenging processes, which we perform today with more than 300 employees at our factory in Saarstedt, near Hanover in Germany. This is the company building. We already started to expand it in 1997, and the last expansion is the part on the right side, where the most of our production departments for Nitinol components are located. The planning for the next building is already ongoing, so that we will have even more production capacity in the near future. Our company is divided in two different business units. One is related to MedTech and the other one is called Metalworks. The Metalworks group concentrates on industries like automotive and filter industry, and they use big metal sheets or tubes for the production of different components. MedTech means that we manufacture, for example, cardiological or urological devices as a contract manufacturer for our customers. And one really important point might be for a lot of you that our ISO 13485 certified quality management also passed the FDA inspections. But what kind of devices are we actually producing, and how does the production process look like? In this overview, you can already see several implants like stents in the bottom center, surgical instruments, and even orthopedic devices that we produce. Now let's have a look at the key facts of our production capabilities. We are one of the pioneers in the stent manufacturing and started with laser cutting cobalt chromium stents in 1995. A few years later, stents made out of Nitinol joined our production portfolio. And today we are a globally active company, and most of our exports go outside of Europe to countries in the rest of the world. With our comprehensive material experience and usage of serial production machines for both prototypes and serial production, we provide full flexibility for your device. Additionally, the 24/7 manufacturing and the rapid production option even enhance this flexibility. And therefore, our processes are adjustable to almost any design. Let's go through the general production process, which most of the devices we produce follow. The first step is the laser cutting. We also offer laser drilling and laser welding, and in all those processes, we perform an in-process quality control, which allows us to achieve a superior dimensional accuracy. As a following step, we are able to heat treat or shape set your medical device. Of course, it depends on the material which process we apply. Afterwards, a lot of medical devices need to be electropolished. Our machines allow us a widely adjustable range of material removal. And for the subsequent passivation, we use an automated cleaning line to reach consistent results and to enhance the biocompatibility of the components. Finally, each part needs to pass quality control. We perform a 100% visual inspection of all implants and own several different automatic microscopes for further controls. And you can already keep those symbols shown here in mind. You will see them later again when Kai is going to focus on each single production step a lot deeper. Additionally, to the already mentioned laser material processing, we offer the possibility to 3D print medical implants since the beginning of this year. This is really useful, for example, for customized bone replacement, such as the ones applied to the skull on the left. But a lot of different applications are imaginable, and particularly for complex geometries and components with undercuts, as you can see here in the rotor of a heart pump, which you see on those 4 other pictures. And if you have any request or any design in mind, please let us know, contact us, and we will check our possibilities to help you. I should also not neglect our R&D department. It might be a bit unusual, but we are quite broadly positioned and also have been researching in the field of material science for about 15 years now. We offer, for example, our own resorbable material, which is called polymedics, and Resoloi, a magnesium material, but as well Vasculoi, which is a nickel and cobalt-free material for stents. And furthermore, we also refine our production processes, for example, with different surface conditionings, which we are able to apply during electropolishing. MeKo is known worldwide for manufacturing implants like stents and heart valve frames at highest precision. And each one of those implants actually started out as a prototype at some point. And our customers value our rapid prototyping as follows. It's really great to have production parts at rapid prototyping speeds. Very cool. And there's, in the end, no better way to sum up MeKo's prototyping services than this customer's quote. From the very first iteration on, we treat the prototype the same way as we treat serial production parts, using the same machines and process steps. Like this, we make sure that the prototype is as close to a serial production part as somehow possible from the beginning. And this not only provides customers right away with a good feedback of where they are at in terms of long-term feasibility, but from our experience, it also leads to a very smooth and efficient upscaling process. Since there is no further change in equipment, it's easy not to have unwanted delays, for example. Being able to assist and guide customers very early on by offering quick and high-quality prototyping services is of utmost importance for us. Naturally, every prototype starts with some kind of raw material. That's why MeKo, over the 30 years of its existence, has continuously built up a very substantial material stock. At the moment, we have more than 2,000 different material lots in stock. And as you can see here on the list, it obviously starts with the established cobalt chromium stents and as well stainless steel, but also includes Nitinol and different bioresorbables like our own materials, as I already said, Resoloi and polymedics, but as well Vasculoi, which was specially developed for patients with nickel allergy. And to secure the quality of the material we use here for your products, we perform an inspection of all incoming material. Yeah, that was my part, and now Kai will continue with Nitinol.
Yes, thank you. Thank you very much, Laura, for the summary of our possibilities. So my name is Kai. I am head of production here at MeKo, and I would like to guide you through a couple of our possibilities. Right. Okay, nickel titanium, unlock the full potential of NiTi. Why using nickel titanium? Nickel titanium is an intermetallic bond of nickel and titanium. Preloaded stress is making the material flexible and springy, and this is leading to the known superelasticity that we all use. So nickel alloy is reverting to its original shape after deformation. So first, if you cool it down, you can deform it. It stays in the magnesitic state. And if you heat it up again, it would recover to the original shape that was drained before. So there will be the thermal shape memory. And you also can use this superelasticity if you are keeping it in the austenitic state. You deform the part, it would easily deform up to a certain level, 8% roughly. You can put it in the cassette, for example. If you pop it out, it would recover back to the train shape automatically. This would be the mechanical shape recovery. So we can adjust these shapes by thermal processes. And we also need to take care on specific properties of the material. So this is how we assure that the mechanically desired properties are given at a defined temperature. So here with medical, very often this is the body temperature where the part need to work. So this is what we adjust before by adjusting the AF temperature. So this ability plus the excellent biocompatibility makes the material simply perfect for many medical applications, as there's also no alternative of a material that can do the same. So typical products made from Nitinol. Yeah, the production portfolio is strongly increasing. That's what it is. Actually, we see so much new products. It's getting smaller. So we go with stents a lot in neurological. Of course, we have classical peripheral stents. The thrombectomy is a big field. We do valve components or valve-like components like aortic valves, tricuspid, mitral, heart valves. So they very often are put together from more than one part. So we apply welding, or we even put different frames into each other and connect them. We also do quite a bit of occluder, stone baskets, or guide catheter extensions, where we even weld them together with some classical materials like MB35N, just to have a shaft and a working component at the tip, which is made from the Nitinol. Yeah, precision is our profession. So what is required to manufacture reliable medical components made from Nitinol? Yeah, of course, it is the professional manufacturing, but it's also the related test, because you want to assure that all is correct and all is working as desired. And this is required quite a bit of testing around, and we will speak about this later on. So this is also an important part of my presentation. So, and of course, a good understanding of the material in relation to what you really want is essential. So let's speak about key features. So, of course, all starts with the laser. The cutting quality matters, and it is not only dimensionally, obviously. So for laser cutting, we apply different kind of laser systems. So the early years, it was all lamp pulse. These days, it's all classical fiber lasers, and we also do quite a bit with short pulse lasers. So it's not necessarily one or the other system is better. So the key is use the most suitable system. So a medical product need to be competitive at the very end, because price matters, like always if you do some stuff the commercial way. So what is nickel titanium? It's heat sensitive primarily. So you need to take care on the features of the material, and that means you need to avoid heat. Beside that, of course, dimensional accuracy, service quality is essential. So you don't want to have burr on it. You don't want to have oxides. You really want to keep the material clean. And we can work with typical tolerances in the range of ±10 micrometer. So if we refer to the pictures you see, let me switch on the pointer. So you have a typical laser cut part as it comes from the laser. Then you have a SEM picture just of the cutting edge. You see it's already pretty clean. You have light microscope pictures as well, just to give you an impression how it would look like. But what you see is you have the sharp edges, and you have some original size stents just as a nice addition of a picture. Okay, welding. Welding is also a technology that we do with the lasers, and welding is beneficial. Of course, that sounds logical somehow, but welding is very beneficial as it prevents critical scenarios like contact corrosion or friction causing to nickel leaching. This is for nickel titanium. This is very important. So because you don't want to harm the surface, or you also don't like to have a constant level of nickel leaching out of a contact of two materials. So therefore, welding is a very efficient and reliable solution. On the right hand, you see two nickel titanium wires that we weld together in the middle. See? And then on the right hand, we have a higher magnification where you can see the weld itself. There's no foreign material. This is all base material. Molten. We lose a little bit the mechanical properties inside the weld. Of course, that's the nature of the welding. But other than that, we can cover this by adding a smart way of welding the materials together. So always have intact base material, and we have the strong connection by the weld, so that the part itself is getting a stable and long-lasting connection, even under conditions inside the body. So typical weld combinations is nickel titanium, nickel titanium. We do nickel titanium tantalum, nickel titanium MP35N, especially if you have a shaft to connect to the quite expensive nickel titanium material, so that will be beneficial at that point. So of course, other scenarios would be sinkable. Some of them work, some of them are problematic, especially if you need to polish, or if it comes to corrosion situation inside the body. But we also will hear later about that. Yeah, marker welding, that's also a big topic where the weld is finding its application. We crimp or weld marker in nickel titanium to make the parts visible. Of course, the density of nickel titanium is quite low, so you put in a radiopaque material with high density and make the part visible. And you see on the right top, we have a ringlet, a nickel titanium ringlet, and in the middle we put in the marker dot, and on the left, on the right of the marker dot, you see the welds inside the material. So it is a tough connection to the base material, so that there's no risk that we would lose this marker, even if the material undergoes some deformation if put in the catheter. So on the bottom view, on the bottom picture, you see a top view of this marker ringlet. In the middle, again, the tantalum, you see the weld, and you have the ringlet outside. So interesting is, it's not limited to tantalum. We also can use different marker materials like platinum, iridium, platinum, gold, and we can cut this to shape. So for very special application, might be required that you have a unique form of a marker, and we can even do that. We cut off a puzzle piece that fits into the stent geometry. And as an example, we did this card, playing card symbols that we did in a generic nickel titanium stent. So also that is possible. And as said, some of them can be welded and would last. Set to shape, tune the properties. This is a very important topic because precise heat treatments are essential. So of course, we need to thermally set the geometry that the part is getting its later shape for the functionality. So that it gets the right shape for staying in the body, as well as holding a valve, whatever, or the leaflets. So beside that, we also need to adjust the transformation temperatures, because these transformation temperatures, especially we very often we hear about the AF temperature. This AF temperature is principally defining also the mechanical properties at the working point, e.g. body temperature. So this is also done by heat treatments. We do this in multiple treatment steps. That's quite common. And we are using different heating concepts. It's like with the lasers. You're using the right concept for doing the part. So this can be a vacuum furnace. This can be a salt pot bases, fluidized baths, or even air furnaces. All of these scenarios are syncable and find their application. Yeah, shape setting, that's not possible without having precise tooling, because the tooling is what actually keeps the parts in shape pre-heat treatment. And within the heat treatment, you actually train a new shape to the part. So therefore, the tool manufacturing is a key. So we have the tool manufacturing in-house. We are using milling, turning, and especially 3D metal printing. That's quite common. It was getting stronger and stronger over the past years. And of course, we are deeply into this technology. And with our CAD department, our tool shop manufacturing department, we develop the tools from the beginning on. We do our files, and then we bring them to printing so that we can shape set the parts within very tight tolerances according to customer specifications. Yeah, of course, we spoke about the AF temperature. This is very important. Precise measurements of the transformation temperature is very important. So in principle, we apply two different technology. First is the bend and free recovery. It's BFR. I think everybody was hearing that. It's per ASTM standard. And the interesting thing, or the important thing, it is non-destructive. So what do we do with bend free recovery? Actually, we put the part in a liquid, we cool it down in a martensitic condition, and then we start heating up and record the curve. At a certain point, it starts converting back in its austenitic state. So we have the austenitic start point, and then of course the slightly bent shape is recovering back to the original shape as it was trained by the heat treatment. If it is fully recovering, of course, there's no dimensional change anymore, and we would define the AF temperature just by putting some straights on the curves. The cross point is the austenite finish. So we are back in the austenitic. That would be bend free recovery. It is non-destructive, so it's also good for quality inspection, or even if you have a complaint part, just to cross-check it without destroying. But it is also keeping the geometry factor into the race, so because the geometry factor is also influencing how the part recovers. So second method is with a scanning calorimeter, DSC. It is working pretty much the same way, but it is using material samples instead of full parts. So you cut off a little segment of the part, and then you put it into the calorimeter, you cool down, and you see the enthalpy of this part. So whenever something is happening with fast phase transformation, you would see with the calorimeter as a little peak. So here we have the R phase, we run through the R phase, we continue at the end of the curve at a temperature of about -50 degrees. We go into the martensitic transformation. So then we have it in the full martensitic condition. So the secondary martensit, the martensit itself, all is now really in martensitic transformation, and we heat up again. So heating up means we are bringing back the martensit, and we are bringing back the R phase in the final condition, in the final austenitic condition. So here the part, here again, we put lines on the curve. The cross section would define the austenite finish temperature. So these are two different methods. The different scanning calorimeter method is not 100% in accordance to the ASTM F2004. This is because we are using codework material in here. We want to measure active AF. That's always important. So we need to keep the codework in there, and therefore it is having some limits according to the standard. But at the end, if you know what you're doing and you know what kind of material are you putting into the calorimeter, it is a more reliable and much more precise method. As I said, we are not having the geometry factor. We are not measuring the effect from the outside like BFR. We are looking inside the material and do the enthalpy directly. So we have the fast phase transformations visualized by the calorimeter. And that gives us also the active AF temperature, even if we use DSC methods. So electropolishing, that's essential to make the parts implantable. So polishing is conditioning the surface, one mechanically. And mechanically means you are really removing surface defects, you are rounding the edges, you make the part smooth, and you would take out the nickel out of the surface layers of the material. So all of this is definitely caused by the electropolishing process, and therefore it is always mechanically as well as chemically how you affect the part. So the best surface functionality is achieved by electropolishing because it is homogeneous. It is working on the outside, inside, on the strut, on the cutting side of the strut, and it would prevent mechanical load. For example, if you have some stress on the surface due to the laser process, this would be gone. Also, during the process, it is not adding load other than mechanical polishing, for example. You always would keep some load on the surface of the part, and you would bring in a little amount of cold work. That's not given with electropolishing. So, and of course, it is allowing defined material removal rates this is important really to bring the strut to the lighter dimensional configuration that you want. So it's a very important process, and the preferred way to do this is definitely apply electropolishing. Yeah, on the surface. And the question now is, are surface after electropolishing and passivation functional? And yes, absolutely, in many ways. So we hit a couple of them. So it is increasing functionality because of the smooth surface conditions. So it is a stress-free surface that's important. So then we assure biocompatibility. So electropolishing is removing nickel out of the upper surface layers. So you keep the titanium for later on forming titanium oxide. So it's a very important functionality behind that. So this is also done by electropolishing. Preventing corrosion. Yes, if you have a defined surface, a smooth surface without interruptions, it is beneficial for corrosion. So also, if you are able to form a nice layer of titanium oxide, a thin layer, stable layer, it is definitely helping you with corrosion resistance. So, and it's also increasing fatigue life. You remove all the little defects from the surface. So crack initiation is pushed far away compared to non-polished parts. So definitely it is having a good factor on increasing fatigue life. And at the very end, makes the component look nice, which is also important because you want to push it out of the catheter. You don't want to have it scratch inside the catheter and cause a lot of friction. Also in the body, it really should keep the vessel open, for example, or keep the valve stabilized. So you don't want to have a sharp edge that causes irritations and so on. So polishing is really fulfilling this in a very good way. And here, especially electropolishing as the preferred method. Summarizing it, electropolishing passivation, of course, it's an important topic. Electropolishing is essential to achieve high quality surfaces, removes nickel out of the upper surface layer, removes surface-related defects like scratches or potential heat-affected zones, and it is increasing fatigue life. So passivation is finalizing the functionality of the implant surface because it allows to form a thin but very stable layer of titanium oxide. It don't need to be thick. It's just a couple of angstrom, 50 angstrom, about that. So it's further increasing corrosion resistance and assures biocompatibility, without having nickel in the surface, forming a nice and stable level titanium oxide. This makes the part absolutely biocompatible. And if the layer is thin, would undergo flexibility without having open positions for nickelies and so on. So, but we also have methods to prove this. So corrosion can be displayed. That's the topic. So, and tactic potential dynamic analysis, according to a ASTM standard, which is the F2129, is used to study the corrosion behavior of the metallic materials. And of course, we also apply it on nickel titanium. The potential dynamic curve delivers key parameters that tells us a lot about the corrosion behavior. And we can go through real quick. If you put it in the potential stud, you apply a voltage and you record the current, you would easily see, okay, you are running up this line. It's a logarithmical scale, so don't be nervous about that. Seems to be the corrosion, but here we are clearly in the passivation area. So the material is fully passive until we reach the breakdown potential. And here really the passive layer of the nickel titanium material is interrupted. We run into the corrosion section, and you see here the current is increasing. We display it up to a certain level. Then we say, okay, let's go back. This is at about, let's say 1.2 volts. We go back, and then we will expect repassivation. So we see a very close loop that's very beneficial. So we cross the old line, we close the loop. That's the repassivation point, and we are in the passive area again. So the material means even if it goes in corrosion, comes back. So that would be a good case. So let's now look at the other case. We have another graph. So we increase the voltage again, and already at half a volt, we are running into the breakdown potential. So we run into corrosion, purely corrosion. We go back, and we even don't see a repassivation behavior. The material simply gives up. And yeah, most probably struts are eaten away at this moment already. So we stay in the corrosion, and the material does not come back and is not self-passivating. So it means here's really critical. We have a critical situation here. So just as an example that you have seen such a graph, it's way more complicated. But then we have our experts who go in further details here. So at the end, a corrosion rate can be calculated. That's not a bad thing, just to know it. So electrochemical impedance spectroscopy, it's another technology of gaining knowledge about the passive layer. So here we apply again a voltage, measure the current. We calculate the polarization resistance, and it's not the nominal value that is of interest. We just want to see how behaves the part. And if you have a good amount of experience on these parts, you can see that the curve is just stable and is reaching mega ohms. So that's for a polarization resistance, pretty good value. So we would be satisfied with this, and we don't see interruption, especially at the lower frequencies. So that's really a nice curve. And again, this is not really the number itself that stays behind. It needs to fit together. So, and as I said this, we also can look at the phase angle. The phase angle is a thin layer on top of the material. It is behaving like a capacitor. And therefore, we can measure also the phase angle for a capacity. In the ideal case, it's minus 90 degrees. And here we just run to, I don't know, minus 85, something like that. But again, the value is not the most important. We want to see a nice bottom here so that we can assure here's a single layer of passivation and not really a lot of residues, interruptions like big inclusions and all of this stuff, what can cause really a non-smooth curve for the phase angle. So on the bottom, we just gave such an example. So first, if you look at the polarization resistance, you see it runs up, but suddenly it really interrupts. And if this is happening, mostly the phase angle is just doing the same thing. It is also not forming the bottom. It's like a bumpy thing. So that means there are different passivation layer that work against each other. Or of course, alternatively, if you put other materials on the material, that also can cause such a bumpy curve. So attention. So, but this requires really a lot of experience. It's not the absolute number. It is really how look these curves in combination with the potential dynamic analysis, the corrosion analysis. So electroimpedance spectroscopy is not part of the ASTM, but we would always suggest to do this in addition, just to see how is the functional behavior of the passive layer. Do you have one single and compact layer of passivation on your part? The last of this set is the galvanic potential. It's also the galvanic potential exists if a device consists two or more materials. Stent marker inside the stent structure, that is a galvanic element from the cathode that can cause corrosion. You see on the right-hand side, you see pictures. We put a marker dot inside the stent ringlet, and this can go into this is causing a galvanic potential. It would not matter if you weld it in or you would crimp it in. Definitely here a galvanic potential is caused. And in the worst case, this could cause to corrosion that eats up the nickel titanium part. So, but don't be nervous. For stent-like application, mostly the marker area is negligible in comparison to the stent area. So the galvanic current is so low that the actually corrosion will not occur. But again, it's better knowing than guessing, and therefore we always say, yeah, check this out. Do galvanic potential investigation report can be issued, and then you also have a verification of a working combination. So it's very important to know if you work with marker or if you add materials to your nickel titanium component, where you are thinking there could potentially a galvanic potential. So it is measurable. Potential dynamic analysis, electrochemical impedance plus the galvanic potential, we always suggest use them all. They give you answers and they give you confidence in the reliability of your medical product. So a stent with high breakdown potential is expected to have good corrosion resistance. We work with values higher than as a acceptance criteria, or work with higher than 600 millivolts for stent-like components, which is pretty good. You need to define this somehow. So therefore, we can assist you there. Good corrosion resistance is essential for device life without nickel leaching. The corrosion resistance need to be given. If it is not there and you would eat up struts, there's automatically also a leachage of nickel, and that would really harm essential. So compactness of the passivation ratio assures biological stability of the implant surface. This was also investigated by EIS. So we heard about that. And high protect potential and the associated repassivation is important if the titanium oxide passive layer gets damaged. This is a very important point. You want to have the closed loop. You want to have the repassivation behavior of the implant. So because if you implant it and slide it out of the cassette there, or it rubs against the other strut, it is possible that the titanium oxide layer gets damaged. And then, of course, you need to be you need to be assured that this is not causing too unwanted corrosion. You need to have a good repassivation behavior of the part. So, and again, this can be assured if you were pre-measuring it. So you simply get that confidence. So, and lastly, of course, prevent critical galvanic elements. Some of them are in there. You need to have markers if you want to make the part visible, but you need to cross-check if they are working in your concept. So also different materials would cause different galvanic elements. So you can measure it. Yeah, how do we assure that all of this scene is applied to your component? The important thing is tell us your requirement and allow us to be your partner. We see this always as a partnership because this helps us to develop the reliable products that find their use in a human body. So it is important that we speak about this. And we have all technical trained engineers, customer responsible persons. They easily could refer even to production if they cannot answer a question. So yeah, keep us involved. Our production is offering a wide range of possibility, plus the required testing technology according to up-to-date standards. Again, if we know what you want, we can apply the best possible production process and also the most competitive. So don't hesitate, contact us. Yeah, so back to the question, why nickel titanium? Of course, because of its unique features. So it's really fun working with something with a little portion of mystery. That's what it is. So it's not an easy material, but it is a handleable material. But it is also something that surprises you from time to time. So measuring features is essential. Thank you very much. Okay, Laura.
Yeah. Thank you very much, Kai, for all the information you shared with us today. And it was really great listening to you as you gained so much experience from your work with nickel titanium in the last decades. Thank you for your time today.
You're very welcome.
So before we send you off, some more information about how we will continue. For all those who already thought about how to receive the slides or maybe the recording of the webinar, we will upload the slides and the recording in the near future. If you have questions, please send them by mail. We will use the questions for an FAQ on our website and answer the questions in written. And as soon as we are ready to upload all these things on the website, we will send an email to you with a link to the information. After a short summer break, our MedTech Materials webinar series will continue as well, probably in September. Please check our homepage where we will publish the dates in the next month. And if you have any requests in the meantime, or if you did not have the chance to get an answer from Kai today, please contact us via the here shown channels. You can always send us an email or call us, check out the website, and yeah, as Kai already stated, just contact us. It's always good to have a partnership with you. So thank you for attending the webinar, and we hope to hear soon again from you. We wish you a good day and see you next time.
Thank you.